Greetings and welcome back. Today we'll be looking at Fischer projections. I know that this video is interjected amongst our different relationships. However, in order to fully explore and understand the rest of the possible stereoisomers, we really need to get a firm grip on what Fischer projections are and why we should be able to use them from time to time. So Fischer projections are our best way of turning three-dimensional molecules, especially chiral carbons, into two dimensions. And this allows us to more easily be able to see what something is. So this is what Fischer projections look like. And what they mean is this. The things on the side are coming out at you. The things on the top and the bottom are going away. So for instance, you could have had, let's say, a CH2OH up here, CH3 down there, an OH off to the right, and an H off to the left. And what that really means is this. And so, in essence, what is on the right is the correct three-dimensional orientation of the molecule, but what's on the left is just a simpler way to express it in two-dimensional space. So the way that we normally draw molecules with our our wedge and our dash is that if we have an sp3 carbon, it would look like this. Let me show you really quickly how we can turn this into a Fischer projection. So let's say that I have an aldehyde up here, CHO. I'm going to put my CH3 down here. We'll put, I don't know, a chlorine right here and an H going in the back. So essentially what we want to be able to do is to figure out from what orientation should we look at this molecule so that the things coming out at us on the sides, right, just like these guys, the things on the side are coming out at us and the thing kind of above and below is going away. And for the sake of this molecule down here, the way that we would look at it, or the perspective we should use, would be from down here. So imagine this is you, and you're looking at it from that perspective. Well, the H and the Cl would be coming out at you from the sides, kind of like they're giving you a hug. And the CHO would be up at your head, and the CH3 would be down at your feet. The reason we do it that way is what we like to do with a Fischer projection is put the carbon chain going straight from the top to the bottom, and furthermore so that carbon number 1 is at the top and whatever your final carbon is down at the bottom. The same thing is happening for this one. That would be 1 because it has a functional group. I know we haven't oriented aldehydes and their naming into our vernacular yet, but that's okay. We can tell that's the only functional group, so that must be at number 1. So that's looking down at us like that. So if we turn this into a Fischer projection, and we'll do it this way first, from that little purple person's point of view, the CHO is at the top because it's at his head going away from him or her. The CH3 is at the bottom. And from that guy's point of view, and you can imagine yourself laying on that purple person's point of view, or if you're watching this on a phone or a tablet, feel free to pick it up and look at it from that point of view. The Cl is coming towards that person, and it would be on his or her right. So the chlorine would be over here, and the H would be on the left. All right, and so when we turn this into a Fischer projection, which is basically what we've done, we would have the aldehyde at the top, the CH3 at the bottom, Cl to the right, and the H to the left. Fischer projections are pretty cool to look at because by looking at it right now, you can definitely tell that that carbon in the center is chiral, and it has exactly 4 substituents, all of which are different. Furthermore, if you put the carbon chain straight up and down, there's only 2 possible ways to look at a Fischer projection, and that is straight up or straight down. So the other thing you can imagine is that we have another person kind of doing this and looking at it in that direction. And in order to do that, you would have to rotate the entire thing around 180 degrees. And so this would also be a correct Fischer projection of the same molecule, but there's really only 2 ways to look at it. If we do it kind of our traditional way like this, with the carbon number 1 at the top and carbon number 3 at the bottom, so going from top to bottom, you get the gist, and that's the general way that we do this. All right, so this is kind of silly though, I would hope that you realize, for 1 carbon, because this molecule right here, we can already figure out if that's R or S. We know how to do that. We can already tell that it's chiral because we can look at this carbon and see that it has 4 different substituents. So Fischer projections are frankly a little bit silly to do with only 1 chiral carbon. However, when you have relatively large molecules, that have multiple chiral carbons, so if you had this thing right here, and we'll put another OH right there, this would be extremely hard to deal with in three-dimensional space because there's so many other substituents. There's 3 different chiral carbons, there's H's and OH's everywhere, and I would say that trying to imagine that in your head and figure out whether that's chiral or not in your head, and given another molecule, can you figure out if they're enantiomers or diastereomers? It's really hard to do that in your head. So Fischer projections are really important, and they really shine for molecules with greater than or equal to 2 chiral carbons. So for 1 chiral carbon, we generally do it this way. For multiple chiral carbons, we tend to turn it into Fischer projections. I'm going to draw a molecule kind of like on that last page with 3 chlorines, and what we are going to do is together turn it into a Fischer projection. When we do that, we can really work with it. We can tell whether or not the molecule is chiral, and again, you might remember, as we've done in lab, that if you have greater than 1 chiral carbon, you never really know whether or not the molecule is chiral or achiral unless you actually make it and look at it. So there is no hard and fast rule. And once again, if you have more than 1 chiral carbon, Fischer projections are the way to go. So what we need to do is look at this guy from the perspectives so that the things on the side are coming out at you, and what's above and below are going away. So I'm going to draw in all of our hydrogens. And what we're going to do is we're going to number this chain. In this case, I don't have a preference. Right or left doesn't really matter in terms of actual nomenclature. So we'll just do it from 1 to 5 this way. All right, so for carbon number 2, we would like to look at it from a perspective where the Cl and the H are coming out at you. And so we'd be looking at it from underneath like this. But you need to imagine that carbon number 1 is at your head and carbon number 5 is at your feet. So we would have a little person like this. And from that point of view, the Cl and the H are reaching out towards the person on the sides, and number 1 is up at its head, and number 5 is down at the feet. All right, for carbon number 3, if you look at these two things, the Cl and the H are sticking up. So the person would need to be looking from the top down so that they would be coming out towards you. So we would have a person up here looking down in that direction. And then for number 4, which will be our final chiral carbon, we would once again look at it from the bottom. So notice that in all of these cases, the person's feet are down at number 5, because 5 should be at the bottom, and number 1 is at the top, because that's where the person's head is. And that's the way that we do this in terms of a Fischer projection. We do it top to bottom. So let's draw this out. From top to bottom, we would have 3 chiral carbons, so we'll put in 3 of these little cross pieces. We have a CH3 at the top and a CH3 at the bottom, and I'm going to go ahead and once again number all of my carbons. So it's 1 at the top and 5 at the bottom. All right, so let's go back into that person's perspective and say for carbon number 2, this guy's looking straight up. So imagine yourself laying underneath of this molecule with your head on this side and the feet down on this side. And as you look at that, basically Cl and H are reaching out towards you, but Cl would be on your right and H would be on your left. This is something that's easier to practice with molecular models, but it's something that you need to be able to do eventually without them. All right, likewise, let's move on to carbon number 3, looking down from the top. The Cl is coming out toward you right now where you're sitting in front of the screen. So if you were laying in that direction, or once again, you can pick this up and move this around if you have a tablet or a phone or something like that. Or if it's a computer, feel free to crawl up on the desk and look at it from the top. The Cl would be on that person's left. The H would be on the right. All right, and then finally, for number 4, it ends up being just like number 2. You're looking at it from below. The wedge was on your right. The wedge is still on your right, but this time the wedge is an H. And therefore the dash, which was going backwards, would be a chlorine. So what we have done is turned this molecule from a 3-dimensional structure, which is a little bit hard to completely wrap your mind around, into a 2-dimensional molecule that we can see, and that is a Fischer projection. And with a Fischer projection, if you want to know whether or not the molecule is chiral, you just look for internal mirror planes of symmetry. And these are very easy to find because there's only two possible internal mirror planes of symmetry. One would be straight up and down, so we can imagine an internal mirror plane of symmetry right here. And the question would be, is everything right and left perfectly flipped or perfectly symmetrical? And in this case, of course, that's not true. This is not an internal mirror plane of symmetry because these two are not exactly the same. These two are not exactly the same, and these two are not exactly the same. So the only other potential internal mirror plane of symmetry would be right here. And so is that reflected perfectly, the top and the bottom? And the answer once again is no. This CL and this H are not the same. This H and this CL are not the same. Even though these two CH3s are reflected perfectly, what's on the sides is not. And therefore, there are no internal mirror planes of symmetry, and the molecule is definitely chiral. Yes. And that's all there is to that. These, once again, with lots of chiral carbons, the odds are that the molecule is going to be chiral, but it is not always chiral. So we have one more thing to define, which is a meso compound. A meso compound simply means that it is an achiral molecule with chiral carbons. So molecules with chiral carbons are often chiral, but sometimes they're not. And when they're not, we call them a meso compound. An example of a meso compound would be something like this. CH3. So notice that this molecule has two chiral carbons, but if you draw an internal mirror plane of symmetry right here, what's reflected above and below are identical. Therefore, this molecule does have chiral carbons, but overall the molecule is achiral. And therefore, we would call this molecule a meso compound. All right, please practice this, and then come to class with any questions. I will see you soon.